big data tools, and welcome to the special assignment 4 report live from Copenhagen. On today's news, Billy has missed his train and was late for work once again, followed by the weather. In our main story this afternoon, Billy, 29 of Vognmandsmarken, had yet again had difficulty with the Danish public transportation system. He rushed to get the train, but from the time he had left his house to the station there had been problems on the line. The lack of real-time analysis and feedback available on the status of the Danish train network system has once again proven to be outdated. The batch processing told him when the train should have arrived, but sadly the real world moves faster than this. Luckily, Billy has now made it to the studio and it's time for the weather. Billy.
Thanks, Casper, and hello everyone, and welcome to the weather. As is typical for this time of year in Copenhagen, the weather will be stormy, wet and windy. But actually this might not be such a problem. This might actually be the solution to what Casper has just discussed.
As you can see from the forecast, Copenhagen should prepare for an Apache storm from Monday onwards. But this isn't any old storm. Apache Storm is a free and open source distributed real-time computational system. Storm makes it easy to reliably process unbound streams of data, doing for real-time processing what Hadoop did for batch processing. Not only that, Storm is fast, scalable, fault-tolerant, and some may even say it's fun to use. The fast processing can be done with over 1 million tuples per second per node. As with most software nowadays in this realm is free and open source, it includes distributed runtime and intuitive APIs for defining distributed process flows. And last of all, it's easy to use and simple to set up.
Wow, perfect, but forgive me for being cynical. Is it really that easy to set up, Billy?
Well, as with any data analysis system, a certain level of knowledge is required, and things do go wrong. But given the big data tools audience for this broadcast, I don't see that being a problem. The setup requires you to install Zookeeper, which I personally had no problem doing. It's worth considering though, you must set up a supervisory process that manages each of your Zookeeper server processes. The Zookeeper server is designed to be fail-fast, meaning it will shut down if an error occurs and that you cannot recover from. That said, don't forget Zookeeper serving cluster is highly reliable, meaning that although the particular server may go down, the cluster as a whole is still active and serving requests.
So is Storm really all I need? Does it solve all my data processing problems, Billy?
Well, that's a good question, Casper. And to which the short answer is no, you'll still need batch processing using a tool like Hadoop with Storm for the real-time element, as the diagram you should be seeing now shows. Many of the larger jobs that are less time reliant can be done behind the scenes in batch jobs, saving Storm for the real-time information.
Okay, but can you tell me how this is different from Hadoop?
Wow, you're really putting me to task on this, Casper. I think it's best if I break this down into two answers. It works, the Storm topology, works in a comparable way to MapReduce. It consumes streams of data, processes those streams, repartitions the streams between each stage of the computation. The key difference to MapReduce, or probably to get back to the question Hadoop, is that both of those have an endpoint, where the data is passed back to the originator, whereas Storm is continuous, i.e. it receives the data non-stop and is set up to do so.
Okay, but what do you mean by topology exactly?
I think to explain that I'll have to introduce some of the Storm terminology. A topology is a graph of spouts and bolts that are connected with stream groupings. As I'm sure you're aware, Casper, spouts will read tuples from an external source such as a database and push them into the topology. Bolts are then used for anything from filtering, functions, aggregations, joins, talking to databases, and most of those kind of things you can think of. Then lastly, we have the stream groupings. They specify for each bolt which streams it should receive as input. A stream grouping defines how that stream should be partitioned among the bolt's tasks.
And what languages are currently supported?
Well, the developers at Storm suggested that Storm was designed from the ground up to be usable with any programming language. As the central part to the core of Storm is the Swift definition, and since Swift can be used in any language, topologies can be defined and submitted in any language. And the same is true of the spouts and the bolts. They can be defined in any language that you want. Non-JVM spouts and bolts communicate to Storm over a JSON-based protocol. Adapters that implement this protocol exist in Ruby, Python, JavaScript, and Perl at the moment. You will find that a lot of the examples online are in Java, but there's becoming more and more support, especially for Python.
Great. Can you give me a coding example to help the viewers understand what's going on here, Billy?
Sure, no problem. Let me just bring up an example on the screen now. This example is taken from GitHub. It's a simple random word counter, and I would encourage anyone to go and take a look at this. It's actually also linked to from the Apache Storm website. So, just to take you through this line by line, the first line there begins with the declaration of a new topology using the topology builder. So almost in every code that you write, you're going to write that kind of line at the top. The next line, at line 3, actually sets the spout. What you're passing into the set spout here is both the name, which in this case is spout, and then an instantiation of random sentence spout, which is essentially emitting 5 random numbers five random sentences as its data. The 5 argument at the end of the setSpout method is a parallelism hint, which is easy for me to say, obviously, or essentially the number of tasks to create for this activity. Once we get onto lines 5 and 6, first the bolt is defined using setBolt, which should be obvious to anyone who's done any coding before. In this case, the map or split bolt. This bolt uses the split sentence to tokenize the input stream and admit its output in individual words. The important thing to note is the shuffle grouping at the end of line 6. This defines the input for this bolt, in this case, which is obviously the spout, but it's defined as shuffle. The reason for this is that the shuffle grouping means that the input from the spout will be shuffled, as you would expect, i.e. randomly distributed to tasks within the bolt. Then we go on to lines 8 and 9. The last bolt is defined here, which is effectively there to reserve, if you were going back to MapReduce, it serves as the reduce element of the method. The word count method implements the necessarily counting behavior, as you would expect, but is not shuffled so that its input is consistent. If there were multiple tasks implementing the reduce behavior, you would end up with segmented counts, not overall counts. It's worth doing that, but the easiest way to understand this and get that bit to work is to try it yourself, test this out yourself. So then on line 12 and 11, we have the configuration object. I'm not going to go into any detail about exactly what this does. At the moment it's enabling the debug mode, but there's a heck of a lot of configuration possibilities and it's worth checking out once you've got into this a bit more. Then we've got lines 14 and 15 to create the local cluster. Again, because this is a local example for practice, it defines the local mode. You give a name to the local cluster, pass in the configuration object, and the topology all created above. Then at the end, we've added added a sleep for a duration, and then the cluster itself shuts down. This bit is obviously not necessarily important, as you don't always need it to shut down, but it's worth seeing how that bit works. So I hope that helps give a good guide to how the code works, but as you all know, you have to go and code this yourself to really get into any detail with it.
Thanks, Billy. I can't really tell this is live TV. This is making a lot of sense to me, as we know, but technology needs to solve like real world problems. So can you tell me, is Storm actually being used, or is it just like on a theoretical base right now?
Yes, there's plenty of real-world examples. Just a quick look at the Apache Storm website, and you'll see going towards 100 projects going on at the moment. Some of the most notable, probably Twitter, Spotify, and Groupon. I think it's relatively obvious to say that with Twitter users generating well over 140 million tweets a day, it's easy to see how this technology could be useful for them if they can analyze things in real time.
Wow, this really seems like it could be the future of real-time data processing, right?
Yeah, absolutely. If you think back in terms of my train delay story earlier in the broadcast, if you think that the storm system could be the one that was doing the processing in order to allow me to view the train's movement in real time on an app, then this would help me to see that the train wasn't on course to arrive at normal time. And this could be way before I had a notification from the train company or from any other journey planner app. In fact, that reminds me, in New York at the moment, there's a project already underway to make this happen.
Very, very interesting. Can you please tell me and the viewers a bit more about this project?
Yes, so the project is based on the NYC Open Data Collection, and it can transform a boring old subway map into real-time "Where's my train now?" moving map. So there's actually a video I can show you, which will play now.
Thank you, Billy, for that introduction. Very interesting. And on that bombshell, it's time to say goodbye. See you next week.